Great, so I'm going to do a problem that asks us to find a general solution for a differential equation that involves trigonometric functions. So cosine of t multiplied by dy dt, and we add to that y times sine of t, and that's all equal to 1. Now for the methods that we use in section 2.2, we want our equation to look like this. We want it to be a y prime plus some function of t times y is equal to a function of t. So it would be a linear first order, and this is just a preferred form. So this cosine is in the wrong place. So the first thing I'm going to do is divide through by cosine of t, and that will give us dy dt is equal to y, plus y times tangent, right? So cosine in the denominator, sine in the numerator gives you a tangent of t is equal to, well, 1 over cosine is also a secant of t. So here is what we actually need to solve. So for this problem, we have two options, right? The first option that we could look for is the Euler-Lagrange method, or we can use an integrating factor. And I think most people would agree that typically integrating factor is the most straightforward in this sort of problem. So when would I use Euler-Lagrange? I would use that if the homogeneous solution was obvious, right? So I can get the homogeneous solution pretty quickly. And then I would use this process, Euler-Lagrange, to get a particular solution. So here we are going to use the integrating factor method. So to get your integrating factor, which is mu, we do e to the integral of whatever is with the y tangent of t dt, which gives you e to the natural log of secant, or just secant of t. So this is an informative mu. What this allows us to do is to rewrite the left-hand side of our equation simply as the derivative with respect to t of mu times y. So mu of t times y. And that's equal, right, on the right-hand side, mu of t times secant, or excuse me, times, secant, where secant is right there, your right-hand side, or sometimes called your forcing function. But we don't have to leave it as mu. We can say, well, we know exactly what this is. Mu, we found that, was itself also secant of t, so maybe I'll color code that. So secant of t there, and likewise, this other mu is also secant of t. So the right-hand side then simplifies simply to secant squared. And so if we were to integrate both sides, we would end up with, on the left, just secant of t times y is equal to the integral of secant squared of t dt, which you likely would know as just being your tangent. Now, it is important to remember to include an arbitrary constant here, c or k, and the reason we use it here and not above is because the integrating factor, when we did that integral here, we're not looking for a general solution for the integrating factor. We're looking for some integrating factor that will do the work for us. And so we just let the arbitrary constant just always add 0, right, to make it a particular one. But now we want to have a general solution, so we have to include the c. So then your issue is, how do I get y by itself? How do I turn this implicit solution into an explicit solution? So we need to divide through by secant. But I think it's also just helpful to remember dividing by secant, since it's the reciprocal of cosine, is the same as multiplying by cosine for our purposes here. So we're going to say y is equal to, you can say cosine of t times tangent of t plus an arbitrary constant times cosine of t. You can simplify it a little bit more since this is just sine of t plus an arbitrary constant times cosine of t. And an arbitrary constant times cosine, that might look a little weird, so it wouldn't be strange to call it c sub 1 or something like that, just to make it clear that it's not part of a trig function. You're not writing c twice on accident or whatnot. All right, great.